Okay, hello. Welcome everyone. Thank you for joining us today for our webinar on a journey through AI-driven efficiency in 5 business sectors. Let me start by introducing myself. My name is Nevra Ledwan. I'm Chief Revenue Officer here at Decision Brain, and I've spent the last 20, almost 25 years now in various sales consulting roles, which means I have been supporting companies in evaluating how to apply a variety of different data and AI technologies to achieve their business objectives. So my experience, I'm focused on optimization here, and that's going to be our focus of today's discussion, but my focus has spanned a lot of different branches of data and AI. I've worked in predictive analytics and machine learning. I've worked in natural language processing, in the pre-chat GPT LLM days. I've worked on what used to be called expert systems and then business rule management systems. And I've done this across different industries. So I've helped companies across the spectrum with, marketing offers and predicting customer churn and underwriting insurance claims or insurance policies and processing claims. I've done a lot in supply chain and manufacturing, both on the planning side as well as the execution side. I've helped investment firms with making investment decisions based on what's written in the news and in research reports. So really, I've had a front row seat in witnessing the different branches of AI. And although I started with business rules and optimization, after going through all of that, I've circled back to optimization. And why did I do that? Not for the novelty, but really for the impact on business efficiency that I'm witnessing. And that's really what I get a lot of joy out of, is really helping make a difference in my customers, helping them achieve their objectives. So I want to share some of what I've learned. I'm basically going to cover 3 topics today. I'm going to give a high-level explanation of what is mathematical optimization and how does it fit into the broader AI landscape. I'm going to talk about what has changed in this field and why is now a better time than ever before to think about embracing optimization if you haven't yet. And throughout the talk, I'm going to intersperse 5 different case studies that I've handpicked just because of their variety of different sort of use cases and industries. So let us flip over into the slides. And I'm going to begin with a quote from a podcast that I really enjoy. Let me flip over. I don't know if any of you have ever read or listened to the All In podcast, run by some, Silicon Valley tech entrepreneurs and investors. But David Friedberg, in an episode late last year, made this comment that I couldn't help chuckle at and agree with, which is, he said, people always ask, what is AI? Well, I don't get the term. When I started my company, I had people I called math people, and then statisticians, then it was called data science, then it was called big data, then it was called machine learning, now it's called artificial intelligence. At the end of the day, it's software-based algorithms that use 3 things: data, software, and statistics. And the statistical tools and the approach to the software algorithm development have changed with the transformer model, but it's the same thing we've been doing since the 1960s, which is creating packages of software that make predictions and that do things for us. And all that's happened in the last 2 years is we've seen a piece of software that can communicate well with us based on these large language models, and we're like, oh, intelligence is here. So maybe some of you can relate to that as well. But we have come a long way, and I'm really excited about where we're already at and also what's coming ahead. So let me also, I forgot to say a couple of logistical things. So first of all, this presentation will be recorded, and you will be able to access it through the same LinkedIn page. Go ahead and submit questions if you would like. The best way to do it is just to put comments into LinkedIn, and Chala, who is my colleague assisting me, at the end of the talk will message them to me. If we still have time, I'll answer them. Otherwise, I'll get back to you. And then thirdly, you're welcome to either chat me on LinkedIn or email me, and I'll have my email address at the end. Okay, so let us go to the next slide. So I'm sure you've seen diagrams like this. I see these all the time. I made this one, but I made it based on, a common model that I see out there, which is, you look at the AI landscape, and what I'm showing here is I'm not talking about the generative part of AI. I'm really focused on the segment of AI technologies that are involved in decision making. So typically you see, there's the machine learning branch and the natural language processing, there's, computer vision and business rules. And I know this is not very complete. And machine learning alone could be a huge branching tree, and supervised and unsupervised, but just very high level. I'm sure you've seen these before. And what always irks me is this is missing, this optimization branch, which sometimes you see a little tiny mention of it, but I don't think that it gets enough of the attention relative to the value it's bringing and the impact it's having on businesses. So I thought to myself, well, the other, I could go around, promoting this infographic here, but I don't know that this is the best way to represent the relative impact optimization is having. So I asked myself, I said, if I were to create a new infographic, what do I want to represent? What really is the goal of AI? And the way I look at it, again, excluding the generative part, which is really exciting and very impactful, but on the decision-making side, really the goal of AI is to take data, turn it into knowledge, and use that knowledge to take the right action. So the data, this is data about your materials, about your inventory, about your employees, your trucks, right? Your sales, your costs. Take the inventory example. You take that data about your inventory levels, and then you turn that into knowledge, which is like, how does my inventory levels, how does that impact my sales and my costs? Okay, well, now I have some knowledge about the relationship there. Now I turn that into action. Should I change the way I manage my inventory, for instance? So I thought about this, and I thought, how would I create a new way of looking at the AI landscape? And this is what I came up with. So really, at the end of the day, the different data and AI technologies are used to help you see, understand, predict, decide, and do. So I want to, I think you can get the slides from me later, you can read this, but I want to give you an example of each of these in the context of a real world situation, which would be take an elevator company, for example. So the first thing an elevator company wants to do, so take for instance, COVID. COVID came, and as you might imagine, people not going into offices, the utilization of the elevators went down. So the first thing as an elevator company, you might, if your job is to service those elevators, you want to see what's being used when, right? So you need IoT and enabled devices and sensors to be able to see what that utilization is. Next, understand, you might want to use some business intelligence tools, maybe some machine learning technology, to see the maybe when does a component of the door opening mechanism break down? Maybe you want to learn that every approximately 1,000 open close cycles of the doors, it tends to break down. So probably a good idea to maintain it before then. Then there's the prediction, which is, okay, based, and by the way, on the learning, you might also understand that in humid areas, it's 800 open close cycles when it breaks down. So this is interesting knowledge that you're acquiring with these technologies. Then you get to the prediction stage, which is where I see a lot of companies kind of stop or kind of go like really, really heavy into prediction and maybe don't make it to the next step. So, prediction is very important. How can I use this new knowledge I have to predict when my elevator units are going to break down? So what I could do is I could, for every elevator I have, around the world, put a prediction on, this is the day when it's going to break down, and then let's back off, however many weeks, and say this is the optimal time to do the service to prevent it. We then get to the decide box, or I guess this is a hexagon, I believe. So what decisions do I have to make? Well, I could decide when exactly is the right time to service each of the units. Who should I assign to do the service? How can I plan that service so that I can carry it out efficiently? What about the contracts I have with my customers, by the way? Should I think about renegotiating those contracts? And instead of saying, I promise to maintain the elevator once a quarter, maybe I want to flip to an uptime commitment, a service level agreement that says, I'll decide when to maintain it. During COVID, I might not come, but twice or once a year because the utilization is so low. But I'm going to guarantee you it's going to be operational at at this uptime level. And then once I make those decisions, then there's the execution, the do part. I don't think that there's robotics being used for this, but the execution system that dispatches my technicians, the technology that shows me the GPS location or real-time traffic data, etc. So the decide box here is in orange, and the reason is, part of it is I like optimization, but the real reason is this is where we as business leaders have the biggest impact on our achievement of our objectives, our business objectives. This is the critical step because it's one thing, a lot of this other stuff, things are happening in the world. It's really hard to control the world, but it is we do have the ability to control what we do about it. And this is why decision support systems and making sure that you also embrace AI to help you, support you in making these critical decisions is so important and impactful. So that's going to lead us into our first case study, which is an elevator company. And this particular use case happens to be about tactical planning. So there's strategic long-term planning, there's midterm tactical planning, and then there's sort of operational planning and scheduling in the shortest time horizon. So this company is doing tactical planning of the maintenance of their elevator units in the field, and they're working toward a global rollout. I think they're past 10 countries and more than 40,000 units in the field. They're using the system to plan. But the idea is I take all of the data that I have and my forecast data about when each unit is going to need maintenance. It's more complex. It's each component of each unit. And then I look out over a rolling 12-month time horizon and figure out, okay, based on that, when is the right time to approximately the right week? I'm going to sort of roughly schedule in when should that maintenance happen. And I'm going to consider different things when I kind of rough it in. I'm going to think about making sure I'm within the right window. I'm not doing it too early or too late. I'm going to make sure that I'm doing it at a time when, if it happens to be a busy vacation week, holiday week, well, maybe I'm going to minimize how many I schedule that week. If it's, let's say there's a big event, that I'm predicting, okay, well, maybe I need to do some of the service, before or after. So this is the tactical planning, and you can see in this image the concept of smart activity bundling, because the other thing that I'm thinking about at the tactical level is how can I roughly plan it so that maybe I'm kind of in the right, similar parts of town doing maintenance, so I can optimize my technicians so they're not traveling more than necessary. So that's our first use case. There's more about this use case on our website. So now let's get into what is mathematical optimization. So I think the easiest way to think about it is to think about all the different places in our life that we usually run into it, we experience it firsthand. So pricing optimization, usually referred to as revenue management or yield management, you see it with how airlines and hotels price seats in hotel rooms. You see it in, Amazon routing their trucks to efficiently deliver your packages. You see it when you go to the store in a couple of ways. You see the way that they choose which items to stock in which stores, and also how they lay out those items. And then you see it in, for instance, if you do any investing and you use any of those tools your brokerage might have to say, if I'm going to retire at this age and I'm not very, into risk taking, tell me, optimize for me how many of which types of investments to have in each risk category. And scheduling is a common use case. I like the airline crew scheduling example because it's I think it's the hardest kind of workforce scheduling I can think about, because you have a lot of both skill matching. You've got aircraft that travels. You want to minimize deadheading. You got to get people back to where they started. It's sort of a classic hard scheduling problem to think about. So that's where we see it in everyday life. If I just take one of those examples, so every one of these, it might look simple here, but every one of these is really complex. And if we take one that's kind of easy to think about, which is routing. So, if I have one mobile worker and I want to visit 5 customers, I think that's 5 factorial. So, 120 possible routes that I can take. Well, with one mobile worker and I've got 10 customers, look how big it gets. And then you multiply that. In the real world, we've got usually hundreds, if not thousands, of mobile workers visiting typically hundreds or thousands or more customers. You start to get into numbers of possible routes that you just cannot sit around and wait for your computer, no matter how powerful, to go through all of the possibilities. You need a smart way to quickly find what is the best, or at least a very, very good route. And so that leads us into the second case study, which is technician dispatching. So this customer is a facility management company that has a division that does, it's a global real estate company that has a division that does facility management in the UK. And they are servicing 20,000 locations with over 1,000 technicians. I think some of these numbers have changed. I think when we started working with them a few years ago, that's what they were at. And what they're trying to do, so take that last example, which was tactical planning, sort of rough cut planning over a 12-month time horizon. Imagine the output of that technical plan is, okay, here's roughly what you're doing, in terms of preventative maintenance per week. This is taking that plan as an input, for instance, and saying, okay, here I am now for the next 3 weeks, create my schedule of who's working when, figure out who to assign which work orders to. By the way, it gets much more complex because I have to match the skills with what is needed in the work order. I also want to consider proximity. I don't want to send someone, too far away from where they are based or where they live. And by the way, now I'm dealing with not just preventative maintenance that I can plan for, but I'm dealing with a lot of reactive work that I have to interleave in. So this also is a difficult problem because there's a lot of interactivity required, because you've got constantly throughout the day, somebody calls in sick, urgent customer, needs you to come today, you got to mess with the schedule. So optimization-based systems are now finally really good at handling these kinds of use cases. And this is another case study that we not only have it as a case study, but we have a recorded demo of a similar application available on our YouTube channel. Go to the next slide. So, optimization, the word optimization is a little bit misleading because it's, it kind of implies, there is the one optimal. But in the real world, optimization, it's really about trade-offs, right? So, yeah, you want to operate efficiently, but you also, I was talking to this company that does some helicopter logistics stuff in the petroleum industry recently, and they were like, well, we don't like the idea of optimization because it sounds like we're not considering, the safety of people. And that's absolutely false. Optimization is about, you have a variety of objectives, and employee safety, employee fairness, workload balancing is important, as important as you want it to be, right? These systems are all configurable. So you decide how much emphasis do I want to put on those versus efficiency versus profit versus throughput versus, CO2 emissions. So this is the whole thing with optimization. And the reason I think you rarely see, I don't know if I should say rarely, but it is not as common to see optimization being used in fully autonomous systems. Typically, these software applications are decision support, meaning there is a human in there looking at and exploring, let me try if I plan this way. Let me put a little more, let me change my focus on fairness a little more. And now let me look at the output. Now let me compare them side by side, the two scenarios. This is typically how optimization-based decision support systems are used. So that leads us to our third case study, which is a telecommunications company. This is a proof of concept we did and are hoping and expecting we'll move forward into production. But they are working on construction or work both new construction as well as network upgrade projects around the country. And what they're trying to decide is which team do I allocate, or which team members and resources, it's people, it's materials, etc., equipment, do I allocate to which projects when? And by the way, if I do it differently, what's the impact on cost and the completion date, given various scenarios? Like, what if we win this other contract to do this upgrade, in this region? What is that how is that going to impact my performance, my KPIs? And then, most importantly, what can I do about it, right? What levers can we pull in order to reduce project time and/or cost? So I'm trying to include a few screenshots in some of these just so you could get like a sense of, look and feel. So in this one, you can see there's not, so this is the output of optimization. So it's creating, there's lots of different views for plans, but you can see this Gantt chart view. So it said, of these 20 projects in this region, here's how I would plan them out so I can get everything done, in as little time and cost as possible. By the way, nothing's happening here. Probably, in this example, there's nobody's available. You can see there's not a ton of overlap. There's a little bit of overlap, and that's based on resource limitations where you can only do so much in parallel. And then you can have different KPIs to measure the goodness of the plan. So this is, so if someone asks you, how long is it going to take to get all of these projects done, right? I think if you count the weeks here, you have a basis on which to be able to say, what this looks like, if I'm reading it right, about 9 months, give or take. And then, you can also report on the expected, I think this is showing the expected cost per site. So now, let's look at this is a second screen. So here's an example of a scenario comparison screen. So what I did is I made two scenarios. So in one scenario, I fixed the cost. I said, what, this is how much money you get for the project. And I said, let the time vary. Tell me how much time. I'm not going to let you hire, expensive contractors. Tell me how much time it would take to get this done. And, is it possible to get it done within a certain budget? And, if so, how much is it really going to impact the schedule? So that's one scenario. And then in the other scenario, I'm fixing the time and I'm saying, okay, it has to be completed by this date. Tell me what it's going to take in terms of cost. So, if I had, let's say, flexible resource capacity. So if I compare these two, what I'm noticing here is it's showing me between these two scenarios that the fixed cost scenario is going to take almost 500 extra days. So I think that's like an extra year and a half. And per project, that translates into about 25 days of delay per project, and 95% of the projects would be late according to this plan. But on the positive side, I save quite a bit. I actually save. So my new cost is 9.6 million, which is a savings of 2.5 million. So that's great. So this is an example of how you explore trade-offs in a decision support application. Okay, so how do you formulate optimization problems? So, optimization problems are a little bit different than, for instance, machine learning is it's about training. It's about, like, let me show you, here's a good plan, bad plan, good plan, bad plan, bad plan. Like, you don't use that method when you're doing planning, right? You use it for other kinds of AI type approaches, like if you're doing classification or prediction. But in optimization, here's how it works. You typically start by defining what are the business objectives, what are the KPIs that I want to maximize and minimize: efficiency, cost, waste, miles driven, for instance, idle time. And then what is it that you're solving for? So typically the use cases I see most these days are usually around planning and scheduling. So that means what you're solving for is, how many of which products should I produce and when? How much of what inventory should I stock where? What route should I take for each vehicle driver, when, in what stop order, etc. So that's what you're solving for. And then third, what are the constraints that should limit the solution? So you might have precedence rules or space constraints. And there's a cheat sheet on our website I've linked to here that you can go to learn more about this. So now the reality is I'm not going to mislead you into thinking this is super easy. Modeling optimization problems, it does get very complex. You've got a lot of different modeling approaches. You've got different technologies that help you do this. Usually this is very experienced PhDs in operations research that do this kind of modeling. And you also have a variety of algorithms that are used. A lot of the modern commercial solvers today have these algorithms embedded inside, but it can get complex. And the reason for this complexity is in the real world, as I mentioned, these problems are huge and they're really hard to solve. And so you need this mathematical approaches to be able to make it possible to quickly get to a good solution in a reasonable amount of time and compute cost. So because of these complexities, this is why people usually have this reaction, the idea of optimization. Not everybody is using it. It's, it can be intimidating, but we've come a long way. And there have been a number, just as, natural language processing has come a long way, right? We have Hugging Face and we have the transformer model. Similarly, we have all these technology enhancements that have made optimization more accessible than ever. So a couple I want to draw attention to is optimization models. So there are a lot of pre-built, and we actually at Decision Brain have a library of, I think we're up to 20 or so pre-built models for common kinds of like technician dispatching or manufacturing scheduling that we can use as a starting point to bring custom solutions to market very quickly. And then there's also another big, development is these application development platforms that make it easy. One of the challenges is, the companies that are able to employ an army of, PhDs in operations research, they're usually not so good at taking their models and then turning it into a business application that the business can use. So they usually need to rely on IT. But we now have application development platforms that make it possible to turn it all into a nice enterprise-grade application. So, and that's kind of the approach that we take at Decision Brain, is using all of this technology to quickly bring custom solutions to our customers in a fraction of the time that it used to take, and for about the cost, sometimes less even than comparable packaged applications. But the difference is that even mid-market companies now can have custom fit decision support applications without being limited to just the packaged applications on the market or having to hire their own operations research experts. So the last two case studies I want to cover, one of them is in the manufacturing side. So I picked this one, which is this is a provider of automotive parts. So they do injection molded bumpers and side rails. And what they're doing in this first project is, it's something that on the surface people think, sounds easy: paint sequencing, right? How many white bumpers do I make and when do I switch to red? And, it takes 4 hours to, for the paint layers and the primer, to cure. So how do I optimize this process? And by the way, what's coming out of the injection mold step is varying, and oops, the machine stopped, and so now I have to change the schedule. So it gets complicated, and this is what I've seen in manufacturing across many industries, is what on the surface may look like a very simple problem. Once you get into it, you realize that, on this carousel, you have these masts, and they have these clips that are custom to every manufacturer's unique bumper shape. So if you want to switch from a, I'm going to make up, Ford to a BMW type bumper, you have to manually go and make the change, and that takes a while, slows things down. And you don't want to be running masks through empty if possible. And by the way, you have to consider that when you switch to white, you have to do extra cleaning versus the other colors. So what we find is that a lot of the ERPs, right, and MESs, they may have APS, or advanced planning and scheduling solutions that bolt onto them, but usually they're not flexible enough to be able to meet most a lot of the requirements in the real world. So many companies end up either going to manual spreadsheet-based scheduling, or they come to somebody like us to develop something custom. And then the last case study is, this one is a big company, but just as a last example, is an automotive company that well known for lean manufacturing, and we're helping them bring the lean approach to their inbound logistics planning. So in this case, they have a fleet of about 100 trucks. They schedule about 100 of them a day. They are bringing in parts from about 500 suppliers that are in driving distance to 5 different assembly plants. And what they're doing is they're optimizing which parts do I pick up from which suppliers in what order, such that I can bring to the production line just in time, just in sequence. And they are also optimizing the way that they load the trailers so that they fill the trailer as much as possible and things don't jostle, but they have to consider stacking rules, rotation rules. And this is another case study we have on our website, and there is also a video, I believe, if you want to see a demonstration of the application. So let me stop there. And one last thing, we have a great resource on our website if you want more inspiration for other use cases of not just mathematical optimization, but some of these other branches of AI. So what you can do is click on any one of these boxes inside this wheel, and it opens up a list of some example use cases. So enjoy that. And like I said, contact me with any questions. Feel free to email me or chat me on LinkedIn. And if I don't know we have more time, but if you have any questions, I think because of the time, I will have to get back to you with them. So thank you again.